Hello everyone. In this video we are going to be going over Lab 7 on normal modes, but first we have to do a little lab prep so you guys understand what's going on. In lecture we talked about traveling waves. For example, the green and the blue wave in the GIF at the top are traveling. They look like they're moving. Green is moving to the right, the blue wave is moving to the left. And we also learned how they can combine with each other to make a new wave. In this case, the red wave is the combination of the blue and the green wave, and we say that it's the superposition of the two waves. What's interesting about the red wave is that it has this wave motion, but it doesn't actually look like it's moving either to the left or right. You just have motion going up and down. Now, this isn't the case for all pairs of waves that are moving in different directions. It really requires two very special waves. So let's see if we can do this in the simulation. First, recall from lecture that when we have a string that's fixed at one end, when the wave hits that end, it reflects, and when it's fixed, the wave becomes inverted. So if we send a wave down the string, it's inverted when it hits that right end. Now in this case, actually, the left end is fixed too once I stop moving the wrench, so every time it hits the wrench, it also inverts. Now what I'm going to do is wiggle the wrench and send a wave down the string. When that wave reflects, it will be a traveling wave that's moving left. While that's happening, I'm going to wiggle the wrench again and send another traveling wave to the right. So here's the first wave. Going right. When it reflects, I'm going to send a second wave. Okay, so you had two waves going in opposite directions. When they reach each other in the center, for a brief moment, you see this up and down motion, but it no longer looks like you have two separate traveling waves. And then actually, after the waves pass by each other, they separate again and they become their own distinct waves. We can see this even more dramatically if I switch to oscillate mode, so the simulation does it for me. So it's continuously sending traveling waves to the right. As those waves reflect, you are continuously getting reflected waves to the left. Those waves are combining to give you this standing wave form. So notice that once everything's set up properly, you can't even tell that there's any traveling waves at all. It just looks like you have this one standing wave. That's exactly what we're going to study in today's lab. But before we move to lab, let's talk a little bit more about standing waves. First of all, we define nodes as the places on the standing waves that do not move. So in the simulation up here, you have a node at the center. You have another node a little bit to the left, and then you have a node all the way on the left wall. And you have two more to the right as well. Antinodes are basically the opposite of that. They are defined as the places that move the most. For the red wave, the places that move the most are, first of all, here. So this is where the up and down motion is the most dramatic. You have another one here, another antinode here, and one more right here. We define the mode number for this particular standing wave as the number of antinodes. The symbol we use for that is small letter n, and in this case you have 4 antinodes, so the mode for this red wave would be n is equal to 4. The pictures in the lower right represent standing waves with lower modes. Let me explain the pictures real quick. This first one is supposed to represent a single string that's vibrating up and down. So the middle part goes up to the top. After that, it vibrates all the way back down to the bottom, and then it goes up, and so on and so on. If we were to represent the red standing wave at the top as one of these standing wave pictures, then we would have, we would draw that to represent the wave moving up and down, and then you would have the other half of that to represent the continued vibration. We also might call these loop diagrams. So for n is equal to 1, you have one loop formed by this standing wave. For n is equal to 2, with a mode number of 2, you have 2 loops that are formed. N is equal to 3 is 3 loops, and then for n is equal to 4 at the top, you have 4 loops. Now let's try to understand what the wavelength for these standing waves looks like. Let me clean up a little bit. Okay, so we'll start with n equals 2 because I think that's the easiest. Remember, for the wavelength, we have to trace out one entire repeating shape. So if we start at the left end and we go up, we get to the top, we go back down through the center, we get to the bottom, and then we get back to where we started. So what I've just drawn in red represents one wavelength for the standing wave with n equals 2. Now for these diagrams, the length of the string is capital L, or also the distance between the two walls. So we would say that the wavelength for the n equals 2 standing wave is lambda is equal to L. For the n equals 1 standing wave, we want to trace out one repeating shape. So we start at the left end, we go up, back down through the center, and now we've run out of string, but we still have to keep tracing until we get that repeating shape. So we go down, and we go back up to where we started. So for n equals 1, actually the wavelength is twice the length of the rope, or of the string. So actually in the n equals 1 case, you're only seeing half of the wave. For the n equals 3 case, you start at the left, you go up, down, and then back up to where you started with. In this case, we've traced out one full wave, one full repeating pattern, but we've actually only made it 2/3 of the way across the string. So the wavelength for n equals 3 is 2/3 times L. Notice that in each of these cases, the wavelength of the wave is the same as the length of 2 of the loops. So in the case of n is equal to 2, one loop has a length, let's say small l, and then 2 of those lengths gives you the full wavelength for the standing wave. This is also the case for n is equal to 1. In this case, a loop has a length L, and the second loop would also have a length L, and when you put those together, they have a total length of 2L. If you want to know the length of one of the loops, what you can do is take the full length of the string and divide by the number of loops, or n. This leads you to the formula at the bottom that says the wavelength for the nth mode is equal to 2 times the length per node. Okay, hopefully that makes sense because we will use that formula in today's lab. And without further ado, let's switch over to the lab. And actually, since I still have this simulation running in the background, let's see if we can identify the nodes and the antinodes for these standing waves. So let's give it a second to set up the standing wave. When we do that, we can see that this point right here is not moving at all. So that is a node. Give it a second to stop moving. There it goes. So that's a node. The points that move the most are right here. Here's another antinode, and here's another node. You also have a node at the end point on the right. And for this standing wave, it looks like we have 1, 2, 3, 4, 5. I'm counting 5 antinodes, so this is an n equals 5 standing wave. Okay, this is the original lab packet for the normal modes lab. The first few pages here are things that we have talked about in lecture and earlier in this video. Here you can see the setup that we used for the experiment. On the right side you have a vibrator that's vibrating the string. On the left side you have some weights that are holding the string down. Here they talk about the origin of standing waves. And then here they actually give names to the particular modes that we were talking about. We'll talk about these more in chapter 14. Let's see, the procedure we can skip here, and the data sheet, we have a better data sheet also posted. Here's the procedure page that we used when we were doing the lab. For step 1, we just cut some string. Step 2, we set the frequency of the vibrator to be 120 Hertz. Step 3, we added masses to the string so that 8 loops were observed. The amount of mass hanging from the string represents the tension in the string. Remember from lecture I had this formula where the tension divided by the wavelength squared was equal to the frequency squared times the linear mass density of the rope. So this formula tells us that the tension is going to be important for us in today's lab. Similarly, the wavelength, the frequency, and the linear mass density will all be important in this lab. Okay, so in step 4, we took the measurements. In step 5, we increased the mass hanging from the rope until there were only 7 loops formed. Then we repeated the data taking from step 4, and we continued this way until I believe only 4 loops were formed at the end. Step 6 gives you some information that you'll need for calculations. We used 2 strings for this lab. The first one we used was the thin black thread, and the second one we used was the thick black thread. Here's the data page for this lab. Notice at the top it says Lab 9. For us, this is Lab 7, but Physics 2220 does this as Lab 9. On this page, there are some formulas which we've gone over. There's the setup that we saw in the other lab packet. And let's go over this example real quick. So in the example, there are 6 loops. If you look at the picture above, you have 1, 2, 3, 4, 5, 6 loops. Here you want to measure the length of n is equal to 5 loops. So the red arrow that's shown represents the length of 5 loops. Now, when we made the videos, we actually made a mistake, and we only measured the length of, in this case, it would be 4 loops. So the D that we are using actually represents only the middle loops. We actually skipped the left and the right loops. So for us, if you wanted to measure the wavelength of the blue wave shown, you would take the total length that was measured, D, divide by the number of loops. In this case, there are 4 loops that were measured, and then you would multiply by 2. So the wavelength for the particular standing wave at the top would be 2 times D divided by 4, or 1/2 times D. And that matches up with what you would expect if you were to trace out one of the patterns, one of the repeating patterns. Here the pink line is one repeating pattern, and that's half of the total distance measured, D. The next page is the data table that you will use to record the data that you see in the video. I will help you out and record a little bit of it with you. And then the final page are the questions that you have to answer after you are done taking all your data. Now let's check out the video from the experiment. So this is for the normal modes lab or the standing waves lab. Headless Productions is what the professors at MCC decided to call their production company for the videos that they filmed. Note I was not present in this decision. So the first thing we do is show you the setup for the lab. On the left you have the function generator, the vibrator. On the right is the pulley, and then below that is the hanger where the masses are hanging from. Now let me pause it actually for a second to mention something here. A lot of the info that flashes on the screen only is up there for a few seconds, and you may not be able to read it all in time, so you'll probably have to pause and or rewind the video in order to get all the information you need. We actually show you a video of at least part of the experiment, but we can sort of see a little bit in the picture that's shown here. The darker black regions of the string are the parts that are not vibrating very much, so these are the nodes. The blurry parts are the parts that are vibrating a lot, so those are the antinodes. Okay, before we continue, let me apologize for the annoying sound that you are about to hear. But keep in mind that I had to listen to it for about an hour and a half while I was filming this video, and you guys get to skip it almost entirely. Okay, let's continue. This is the lab actually in action. It's kind of hard to see in the video, but if you were to see this in person, it's actually, I would say it's fairly clear to see which points are the nodes and which points are the antinodes. In the video, you'll see regions that are slightly more dark. These are the regions that are moving less. The most blurry regions are the antinodes. Okay, coming up are the pictures where you'll actually take the data from. Before that, we have this explanation of the mistake that I was talking about. Okay, here is the full setup and how we actually recorded or took the pictures. So I stood in the back and I held up a meter stick. We aligned the meter stick so it was at the node all the way to the left here. We took another picture of the node that is almost all the way to the right, the second most node, right? You have one node at the pulley and we did the one right before that. So then the total distance for this particular standing wave that you want to measure is going to be 97 centimeters, and you'll see why in the next picture right up here. The zero end of the meter stick was held up on the left node, and then that second from the right node goes to 97 centimeters. So then the length is D, capital D is equal to 97 centimeters or 0.97 meters. Okay, the wave that's shown at the bottom has 1, 2, 3, 4, 5, 6, 7, 8 loops. So we're going to say n plus 2 is equal to 8 for this wave. Here we say n is equal to 6 because we actually measured 6 loops. The left end of the meter stick was where my pointer is right now, and the right end of the meter stick was where my pointer is now. So to calculate the wavelength of this wave, we start by finding the length of the loops. So we take the total number of loops, we take the total distance, which is 97 centimeters, and we divide by the total number of loops. So you'll do 0.97 divided by 6, and then you multiply that by 2 to get one full wavelength. And if it wasn't clear, the wave that's shown in the picture at the bottom is supposed to represent the wave that's being formed on the string at the top. If you were able to see this in person, you would see 8 total loops formed, and you would have measured the length of 6 of those loops. Okay, let's see what's next. Okay, here's the amount of mass that we hung from the hanger. So 6 grams were hung from the hanger, and the hanger itself is 5 grams. So we're going to enter 5 plus 6 grams into the data table. And don't forget, we have to convert to kilograms. Okay, and then this is the next part of the experiment, or the next piece of data that we're going to have to record. So let's go back and look at our data table. Okay, so we'll start with string 1, the thin black thread. The first picture showed us a total number of 8 loops, so n plus 2 is 8. What we actually measured were n loops, so 6 loops. The distance that we recorded for the first set was 0.97 meters. And that means the wavelength for that first standing wave will be 2 times 0.97 divided by 6. So you'll get 0.32. 0.32 squared is 0.1024. So we will record 0.1024. The mass that we hung in that first part of the experiment was 5 grams for the hanger and 6 grams for the actual weights. So in total you have 11 grams. But we want to record it in kilograms. So if you have 11 to convert to kilograms, we go over by 3 decimal places. So then 0.011 kilograms is what we measured there. The tension that was in the rope is going to be the force that this mass provided. So the tension T, or tau, or F as we've also called it, is just going to be mass times G. So you're going to take that 0.011 and multiply by 9.8. This gives you 0.1078. Okay, and the reason, by the way, that we had to convert to kilograms was because we want the tension to be in units of newtons. Let's see what else. Down below, we have the linear mass density for the thin black thread. So if we flash back to our the procedure, we will see that the thin black thread had a linear mass density of 0.08 grams per meter. In kilograms per meter, it's 8 times 10 to the minus 5. So that's what we're going to write down there. 8 times 10 to the minus 5. Let's see, this next part, F squared times mu is equal to the tension divided by the wavelength squared. This is going to be the slope that you get from the graph of T versus lambda squared. Okay, so you'll record that value there. This is going to give you the experimental frequency. You take the square root of that slope and you divide by the linear mass density inside of the square root. The frequency from the generator is the value that we had it set to, so that's going to be 120 hertz. And then finally, you're going to calculate the percent difference between this experimental and this theoretical value. Okay, so let's talk about the graph real quick. Once you've watched through the entire experiment and you've recorded all the values in this table, you're going to make a plot with tension on the y-axis and lambda squared on the x-axis. Now, you can do this in basically whatever program you want to use. If you want to use Excel, you can use Excel. I will give you a brief introduction to that in just a second. You can also use the Vernier graphical analysis that we use in class. If you go to Google and you search Vernier graphical analysis, the first link that shows up is Graphical Analysis 4, Vernier. If you follow the link, it'll bring you to the download page where you can download and install it on your computer. And if you have any other favorite programs, you can use those too. All of them will work just fine. But let's assume that I have completed this lab, and let me fill out some data here. Okay, here I've made up some data. Note that this does not correlate with what you will find in the experiment, but let's say that I want to plot lambda squared versus tension here. So then I go to Excel, I plug in all of those values. I have a lambda squared column, I have a t column, and then I write all of the values below that. The next thing I want to do is highlight all of that data. I want to go to Insert at the top. For the charts, I'm going to insert just a regular scatter chart, and that'll give me this. To find out what the slope is, I have to add a trend line. So I'm going to right-click on one of the points, add trend line. And for this lab, we will want to use a linear trend line. Then I want to scroll to the bottom of this window, and I want to display the equation on the chart. Okay, so then on the graph here, it has shown me the equation for this trend line. So this equation has the form of y is equal to mx plus b. The m is the slope of the line, so our slope is 1.0527. So then I'm going to go back to my data table. I'm going to write 1.0527 for the slope, and then I'm going to continue by calculating the frequency and after that the percent difference. Note once again that these are not the values you are going to find for this experiment. These were just some made up numbers. Okay, so you're going to watch through the video, record all of your data, do your calculations, make the graphs, and then at the end you have some questions that you also have to answer. So I think that's all I have to say for you in this video. Of course, if you have any questions, please let me know. Hopefully I've explained this in more than enough detail, but if not, again, please let me know. Okay, good luck.